Okay, welcome to our first lesson in grade 11 trigonometry. So we're going to be working on solving problems with triangles, largely a grade 10 review, and with a couple new things that we're going to see in this lesson. We'll break this up over two videos. First one, we'll introduce the sine law, SOH and the sine law, and we'll talk the cosine law. So this question is just meant for students to think about what kind of situations you can use to solve trigonometry. What tools do we have, and what do we need to use these tools? So what you want to do is start brainstorming some of the things you did in grade 10 and some of the problems that you solved. What were they involving? Like, what kind of applications were we able to solve? So learning goal today is looking at angles or sides in a right triangle in 2D and 3D, solving triangles involving right, acute, and oblique triangles in 2D and 3D. And the right and the acute, that was a grade 10 thing. The oblique or obtuse is actually a grade 11. The 2D is a grade 10, the 3D is grade 11. So you can see how we are going to start to apply this stuff in a new context. We're going to be using sine and cosine law, so those are two of our other tools, and posing your own problems. So just being able to think about the kind of problems that you can solve in the real world. And what situations or what do you need to solve those problems? How are these triangles similar? This is where it all started in grade 10, with similar triangles. So you have to ask the question, all of trigonometry is based on similar triangles. And so the ratios that are in these triangles, the relationships between the sides. And so we're looking at just what relationships are in here. And so the triangles are similar because they have the same angles. All the angles are the same in both triangles. And in fact, you can see that the one is double the other. So it's really just a scale model. And you can't actually draw a triangle any other way. So it has to have those angles if the sides are 6, 8, and 10. The angles are 53.1, 36.9, and 90 degrees. We also have the same ratios, and those ratios are when you divide the sides. So if you do 3 divided by 4 or 6 divided by 8, you get the same thing. 3 divided by 5, 6 divided by 10, you get the same thing. 4 divided by 5 or 8 divided by 10, you get the same thing. Those ratios allow us to actually find, so if you know what kind of triangle you're dealing with, if you know the ratio, they actually allow you to find the angle or a side length. Those are the trig ratios. So we know if any triangle, if you divide this side by this side, and you get 0.75, you can figure out that the angle is 36.9 and 53.1. The trig ratios, we call this one tan, opposite over adjacent, from 36.9. This one's sine of 36.9 is opposite over hypotenuse. And cos of 36.9 is adjacent over hypotenuse. And you can see that it doesn't matter how big the triangle is. The ratio is always 0.8 because it's just a scale of the other one. And so that tells us the angle. So these ratios are actually programmed in the calculator using functions. So we have a sine function, a cos function, a tan function, such that when you input an angle, you get out the ratio. Likewise, you can use the inverse where you input the ratio and you can get an output of the angle if you use the inverse. Use a picture with the angle on top because just wanted to show you that it does depend on where the angle is. So on the last slide, we had the angle on the bottom. But if the angle's on the top, then the side on the bottom is the opposite. It's always opposite the angle. And we also know Pythagorean theorem. H squared equals opposite squared plus adjacent squared, or we've called it c squared equals a squared plus b squared. This is famously known as SOH. SOH, just as a way to remember the order that you divide the sides and which sides give you which ratios. This is a new topic in grade 11. It's a special triangle, and so some angles are used so often that we actually want to make use of exact values. We can use the general form versus decimals in a calculator, just because the angles are used so often. And so the three angles we're going to look at in this unit to do exact values are 45, 30, and 60. So 45 degrees is made from an isosceles triangle of side lengths 1. And if you had side lengths 1, you can actually find the third side. And I invite you to, as a review of Pythagorean theorem, the third side is root 2. The second triangle, so any triangle with a 45 degree angle, you can generalize it and say the side lengths are 1, 1, and root 2. Even if the side lengths were different, every 45 degree right triangle is just a scale drawing or a enlarged version of that exact same triangle. And if we're only looking at ratios, that's all that we need. The second triangle is actually an equilateral triangle. And if you had an equilateral triangle, what would the angles be? And so we know that the angles have to add up to 180, so the angles would all have to be 60. And so that's where the 60 degree angle is going to come from. But how do you make the right triangle? And so if you had a 2, 2, 2, because we're going to cut it in half, rather than using 1, 1, 1, if you have a 2, 2, 2, you can cut it nicely in half and have one of the side lengths 1, and then you have a right triangle. Also, you've created a 30 degree angle on the top because it's an equilateral. The third side of the right triangle is root 3, and you can kind of complete that from Pythagorean theorem. So the second special triangle is 1, 2, root 3 with angles 30, 60, and 90 degrees. So we actually know a whole bunch of ratios. We know sine 45 is 1 over root 2 from opposite over hypotenuse. We know cos 45 is 1 over root 2. Tan 45 is 1 over 1. Sine 60 is root 3 over 2 because opposite over hypotenuse. Cos 60 is 1 over 2 because adjacent over hypotenuse. Tan 60 is root 3 over 1, opposite over adjacent. Cos 30 is root 3 over 2. Sine 30 is 1 over 2. And tan 30 is 1 over root 3. So these angles actually come up often. And so we can see a question like this. Now the question is, could you solve this triangle, solve for the angle, or the side length, which we know is root 2, with SOH? And you can if you split the triangle in half and create right triangles. And then using the trig ratios, SOH, you can actually find the height of the triangle. But the height of the triangle is actually 1 because of the special triangles. This is a 2, 2, 2 cut in half, and so this side length is 1. We also know this side length is root 3, and this side length is 1 because it's a 45 degree isosceles. And if this is 1 and this is 1, we know this is root 2. You can use SOH, but these are the special triangles. Okay, next we're going to talk about the sine law. So this is the sine law. The sine law comes from that exact same example where we cut the triangle in half. So what you do is you cut the triangle, you call the height h, and then we know two things are true. We know that sine b is h over a in the right triangle. We know sine a is opposite over hypotenuse, h over b. We can cross multiply and say that h is a sine b, and h is also b sine a. So that means a sine b must equal b sine a. And then just to make it look a little bit nicer, because this really is the sine law, we can divide both sides by a and both sides by b, and we get sine b over b is sine a over a. And the reciprocal is also true. And this works anywhere in the triangle. So the sine law is basically saying when you divide the sine of the matching of the angle divided by the side across from it, you get the same thing anywhere in the triangle. So you can try this question where you actually draw a side A, side B, and an angle B such that the triangle is acute. So if the triangle is acute, it might look like this. If the triangle is obtuse, it might look like this. If we have 20, 30, and 11, and so that would make sense to have that the 30 because that's the angle that doesn't change. The side length 11, you can see it looks different slightly in the two different triangles. But if you use the sine law to solve for, the only thing you can solve for is this angle, you can say that sine A over 20 is sine 30 over 11. And over here, you say the same thing. Sine of A over 20 is sine 30 over 11. It's no different. And when you solve for it, multiply both sides by 20. Multiply by 20 sine 30 by 20 and divide by 11. You get 0.9091. And so that actually gives you, when you do the sine inverse, 65.38 degrees. We know that's true in the first one, but in the second one, and if you would just watch my cursor, what the calculator is doing is it's actually calculating this angle that I'm making with the cursor, which is the triangle on the left. This guy, if we look at this angle here, that's the triangle on the right. And so what the calculator is not sure what to do, and we'll see this later on in lessons in this unit, what's happening with sine A. But these angles, it turns out, are supplementary of each other. Because if you drew this triangle in here, this angle A down here, if you can imagine, would be the same as this angle here, and these would add up to 180. And so the real angle on the right is 114.62. So when do you have to worry about this? Whenever you have sine theta as a positive number. There's two solutions that could work in a triangle, and this really happens when you're finding an angle with sine law. You have to ask the question, could it be obtuse?